The first oil well was drilled in Titusville, Pennsylvania in August of 1859, and essentially that started the U.S. petroleum age. That was 8 months before the Civil War broke out. But oil was already used long before the first oil well. The easiest way to obtain oil is from oil seeps. Native Americans recognized that they could use tar from oil seeps to waterproof canoes or to treat skin problems. It was the same with the earliest European settlers. There was an awareness of the presence of petroleum seeping out of the ground in places like Pennsylvania, but no significant mining of the product was done. That changed in the 1800s when it was realized that petroleum could be used to make kerosene. On the back end of things, most projections suggest that the world is near or perhaps even past peak oil production. From here on, the search is on for either undiscovered resources or alternatives, and eventually the widespread use of petroleum will end. The famous oil geologist M. King Hubbard wrote in 1971, "It's difficult for people to realize how transitory the fossil fuel epoch will eventually prove to be when it is viewed over a longer span of human history." So regardless, if you're a half full or a half empty person, it's worth taking a look at the geology of petroleum. From the standpoint of geology, petroleum is an amazing entity. Its formation, its accumulation, the obtaining of economically viable volumes, and then innovative uses of the product, all are geologic and technological wonders. Petroleum is Latin for rock oil. Petra is rock, and oleum is oil. These days, the term petroleum generally refers to crude oil, and sometimes more broadly to the naturally occurring mix of both crude oil and natural gas, and that's how I'll use the term. Together, oil and natural gas account for 69% of primary energy used in the United States in 2020. The first natural gas well was dug a generation earlier than the first oil well in 1821 in Fredonia, New York. But it wasn't until the 20th century that natural gas production began to catch up with oil production. Despite the fact that both are found together, the oil industry has tended to treat natural gas as a nuisance to be burned off rather than a high-quality fuel it can become if extra pains are taken to capture and transport it. Petroleum is a fossil fuel. Like all fossils, it is the traces or remains of past life. Specifically, petroleum forms from fossils of organisms found in water. Some petroleum has formed in ancient lakes, but for the most part, it formed from oceanic organisms. Those were primarily planktonic protozoans, some copepods, worms, krill, crabs, jellyfish. Also from the larvae of fish and other invertebrates. That collection of zooplankton combined with diatoms, a phytoplankton that makes up the largest biomass in the ocean, settles out of the water column. As it collects on the ocean floor, it's buried by sediment. As is the case with many fossils, it's critical that burial occurs quickly and in the absence of oxygen, so that the organic material doesn't decay. There used to be a myth that oil was the blood of terrestrial creatures like dinosaurs. That's not the case. All the organic productivity that eventually produces petroleum occurs near the surface of oceans and lakes. All fossil fuels are hydrocarbons, with hydrogen being the valuable part we use for energy and carbon being the leftover waste product. But not all hydrocarbons are the same. Marine plankton is generally comprised of protein and carbohydrates with varying percentages of lipids. That lipid chemistry in the fossils ultimately influences the oily type of fossil fuel produced, petroleum. Once planktonic organic matter is buried, it is broken down by microorganisms. A subgroup of those organisms, called methanogenic microorganisms, use the planktonic organic matter to produce biogenic methane. Methane is the simplest of hydrocarbons, consisting of a single carbon bonded with 4 hydrogens. But the generation of biogenic methane is limited to the upper 3,000 feet of sediment. With deeper burial, there is an increase in temperature and microorganisms can't survive, thus ending any biogenic hydrocarbon production. Below about 9,000 feet of sediment depth, you begin generating the temperatures and pressures necessary for what's called thermogenic generation of gas and crude oil. There are also other components of petroleum generated in the thermogenic process. Nitrogen, carbon dioxide, and hydrogen sulfide show up in varying amounts, and these can cause pollution problems. Also produced are porphyrin compounds, which form from chlorophyll in the phytoplankton. This is evidence of the organic origin of petroleum. Sometimes you'll read about suggestions that petroleum isn't organic. It is. With burial at greater depths, you get increased pressures and temperatures. At around 70,000 feet, oil is no longer generated and only gas is produced. Remember, these pressures and thermal gradients only apply to the formation of petroleum by simple burial. If you involve tectonics at all, then temperatures and pressures are controlled by the tectonic stresses, not by burial deaths. In those cases, the production and destruction, if temperatures get too high, of petroleum gets complex. After the organic matter in marine sediments is transformed to petroleum, the job of the petroleum geologist begins. All the petroleum I have been describing has formed in what's known geologically as source rock. But source rock is only the first of 4 key ingredients to the formation of a large accumulation of petroleum that has traditionally been economically viable, frequently described to investors as an oil play. You want a source rock, a reservoir rock, a cap rock, and a trap. If you have all 4, you have the potential for a solid oil play. A source rock, by definition, is organic rich. But let me ask you, what kind of sedimentary rock makes a good source rock for oil? The organics were deposited in an environment of low energy, so small critters can accumulate, and low oxygen, so they don't decay. Over time, those organics and the sedimentary particles are compressed during the burial process. What do you think results from the compression of organics with sedimentary particles? Shale, right? Probably a black shale. That's frequently what source rocks are. You also find source rocks that are carbonates, limestones, and lake sediments. Almost all source rocks are dark colored. They have a high organic matter content, and a lot of times they have an odor of organics or sulfur. When I was a student, I did field camp in the Four Corners region of the U.S. Many geology programs require a field camp. These are usually a month or 2-month programs spent learning field geology. One of our field projects involved determining how far strata had been offset by a fault. What was critical was the ability to recognize the same rock types on either side of the fault. One of the units turned out to be a petroleum source rock. Of course, it was exposed at the land surface, so most of the petroleum had been oxidized off. But the way we identified it was to break off a piece with our rock hammers and smell it. It reeked of organics and sulfur. The technical term is petroliferous odor. But just finding a source rock is not enough, because frequently petroleum does not stay in the source rock. During burial, seawater is trapped between sedimentary particles of the source rock along with organic material. Petroleum is less dense than seawater. Over time, the petroleum will migrate upward through the seawater via pores and fractures in the source rock. If you're looking for an oil play, you're hoping that the petroleum migrated into a rock with relatively high porosity. These are called reservoir rocks. They can have porosities between 20 and 40%, so they can store a lot of petroleum. Commonly, reservoir rocks are sandstones, fractured shales, or porous limestones. Ancient carbonate reefs make amazing reservoirs. These are all rock types you find in typical marine sequences. So usually when you have a source rock, like shale, you'll have a reservoir rock nearby. Petroleum that has migrated into a reservoir rock is easier to extract than from a source rock. So why doesn't the petroleum continue to migrate on through the reservoir rock? It can. If there's nothing to constrain or impede the movement of the petroleum in the reservoir rock, it will continue to rise upward to become a crude oil seep with the natural gas oxidizing into the atmosphere, even though it's never been burned. During Earth's history, a lot of petroleum has migrated to the surface and dissipated. When you're looking for an oil play, you're looking for an impermeable rock overlying the reservoir rock, and that's called a cap rock. In the groundwater lecture, I talked about clay layers called confining beds or aquicludes. This is a similar phenomenon, with impermeable rock covering the reservoir rock. So is that it? A source rock, a reservoir rock, and a cap rock, and you've got a viable oil play? Not yet. One more ingredient, a trap. Yes, a cap rock will prevent the oil from leaving the reservoir, but frequently a cap is too widespread and oil doesn't collect in any particular place. A trap will result in oil being pooled up in an economically viable volume. Traps occur in all kinds of geologic structures. Essentially, they serve as a place where oil will collect in abundance because of a geologically generated dead end for the migrating petroleum. The simplest to envision is a geologic fold. Rocks are folded, oil goes to the highest point and collects under the axis or arch of the fold. You drill down through the crest of that arch and you strike oil. A successful oil play. Other traps include faults and stratigraphic traps, both of which can have dead ends for flowing petroleum. Another type of trap is a salt dome. I mentioned the formation of salt beds via precipitation in the sedimentary rock lecture. What I didn't mention is that salt beds that form don't necessarily stay exactly where they were deposited and buried. Salt beds can move. Salt is a solid, but it's also capable of flow, like glass or glacial ice. Solids that can flow at temperatures below their melting point are called rheads. The flow rates of rheads are very slow, but nonetheless, they do deform. So salt flows. Where does it go? Below about a mile of rock, rock density exceeds the density of salt. As a result, salt becomes buoyant and begins to flow upward and form a dome. You may have heard about salt domes. In different places, salt domes are used to store valuable commodities. In fact, strategic oil reserves are stored in salt domes. For a while, people debated storing spent nuclear fuel waste in salt domes. But because salt domes flow, it was decided it was not a good idea to put deadly materials inside them. Salt domes are also used to mine salt and sulfur for industrial uses. And salt domes are fairly common. There are over 500 mapped salt domes just along the US Gulf Coast, and they are all pretty much sourced in the Luan Salt. The Luan Salt layer was deposited during the mid-Jurassic, when an isolated basin formed during the initial rifting of North America from Europe. The isolated basin would occasionally be cut off from the incipient Atlantic Ocean, and it would dry out and produce salt layers. Well drillers in the Gulf call the Luan the mother salt bed because all the domes rise up from it. Some of these salt domes can reach a height of 8 miles above the original Luan layer. What does this have to do with oil? As the salt dome rises up and pushes through the sediment, stratigraphic layers will be folded upward. Salt is impermeable, and because the doming process creates dipping beds, petroleum reservoir rocks get pushed up and sealed off. The result is a salt dome trap. You can probably tell that because of the nature of all the geologic traps, oil wells have to be drilled pretty carefully. Not only do you want your drill to hit the oil reserve, but you want to do it in a manner that will maximize productivity. there is a great deal of care taken in the geophysical identification of prospects and the proper drilling of the borehole. The problem with salt dome traps, however, is that geophysical techniques can't always identify the amount of product you will encounter once you get through the salt. As a result, there's a lot of exploratory drilling done in conjunction with salt domes. In 1980, some exploratory drilling in southern Louisiana was being done by Texaco in Lake Penoir. It was a fairly conventional salt dome play. One complication was the drilling platform was set in the middle of Lake Penoir, but the lake was only 10 feet deep. Texaco was aware that the Diamond Crystal Salt Company had a salt mine in the dome. The basic assumption was that everyone understood the configuration of the salt dome, the salt mines, and the reservoir rock they were trying to get into. In retrospect, that wasn't the case. On November 20th, 1980, the oil rig reached a depth of about 1,200 feet. The drill bit got stuck. That's not unusual. But in the process of trying to get the bit loose, a series of unusual events began to occur. First, the drill rig began to shudder and then tip. This is very unusual, and all the drillers abandoned the platform. Next, a whirlpool began to form in the lake. This was something no one had ever seen before. At the same time, in a Diamond Crystal mine shaft at about the 1,300-foot level, water started coming into the mine. That shouldn't happen. Like the oil rig workers, the salt miners reacted quickly to the situation and evacuated the mine. What most people believe happened is that the oil well punctured the salt mine, creating a conduit for the lake water to enter the salt mine. That conduit was enlarged by the lake draining into the mine shaft. It was essentially several hours of chaos that most people consider the worst industrial disaster in Louisiana history. About 3 billion gallons of fresh water from Lake Penoir drained into the salt mine. A canal that led from Lake Penoir to the Gulf of Mexico reversed flow, and salt water began to flow from the Gulf into the lake. Because the lake bed was dry, a waterfall was created, the largest waterfall in Louisiana. There were 11 barges on the lake at the time, and they were pulled by the whirlpool into the now enlarged mine shaft. A tugboat, trees, and a lot of real estate around the margins of Lake Penoir also went down. Afterwards, 9 of the 11 barges popped up out of what was now a 1,300-foot deep lake, the deepest lake in Louisiana. It is a crazy story, but in the end, salt domes in the Gulf remain just incredibly productive petroleum traps. You just have to watch where you drill. So to find oil, you need a source, a reservoir, a cap, and a trap. Combinations of those 4 components are located in well-known sedimentary basins, including the Permian Basin in West Texas and the Bighorn Basin in Wyoming. By mapping those locations, government agencies and oil companies have calculated how much oil exists beneath the U.S. That, of course, is the billion-dollar question. How much oil does the United States have, and when will it run out? It turns out that the answer has changed over the course of the first 2 decades of the 21st century. In 1956, M. King Hubbard, a geologist for Shell Oil, predicted that oil production in the lower 48 states would reach a peak somewhere around 1971. In what's now called the Hubbard curve, he illustrated that all non-renewable resources go through an evolution. It's a bell-shaped curve. Essentially, a resource is discovered, but the technology doesn't exist to use it. As more uses of the resource are developed, the production of that resource increases. Because it's non-renewable, you reach a point where production begins to decline. That means that the cost to use the resource increases. Ideally, alternatives are also found. A non-renewable resource is exactly that, non-renewable. Hubbard and his idea met with consternation. It was pretty audacious for an oil company geologist to predict the decline of petroleum production, but he was absolutely right. All resources go through the exact, or at least very similar, history. So, have we been running out of oil since 1971? The answer is obviously no. In 2009, the U.S. became the largest producer of natural gas in the world. In 2013, the U.S. became the world's largest producer of crude oil. By 2018, the U.S. was exporting more petroleum product than we were importing. What Hubbard didn't know at the time of the publication of his particular curve was that there were petroleum resources that had yet to be discovered and oil recovery technologies that had yet to be developed. From my point of view, compared with when I was just starting out, the newer technologies are absolutely mind-boggling. The petroleum resources that are now being developed were simply unobtainable when I was a grad student. The first big development was the North Slope of Alaska. Production there began in the late 60s, and although steadily declining since the late 80s, it was a remarkable oil play. In the end, over 18 billion barrels of oil have moved through the Trans-Alaska Pipeline, and as a result, extended Hubbard's curve for U.S. petroleum production. The expected peak in total U.S. production occurred in the late 1980s rather than 1971. But the development of hydraulic fracturing and oil production from what are called tight rock formations has essentially offset the decline of Alaskan oil. It turns out that M. King Hubbard was one of the first to envision hydraulic fracturing as a viable method of extracting petroleum product. The oil industry knew there was oil in impermeable units like black shale, but just ignored it. The problem was getting it out economically. If you think about how oil forms, you can envision the origin of tight rock oil plays. Shale is one of those interesting rock types that has characteristics that seem a bit counterintuitive. Shale is porous. That means it has open spaces in it, but those open spaces aren't connected. That means it's impermeable. Lake sediments are made of clay that behave the same way as shale. If you're in a small boat on a lake and you drop the anchor over the side of your boat and let the rope go slack, a minute later a gas bubble, frequently loaded with sulfur, rises to the water surface. What happened? The clay of the lake sediment has lots of pore space, but the clay is impermeable. The decay of organics in the lake sediment results in the production of hydrogen sulfide. The anchor compresses the lake clays and the gas is released and the bubble rises through the water column. So shale is porous but impermeable. How do you get the petroleum product out of the shale source rock? This is a so-called tight rock reservoir. The technology of hydraulic fracturing was developed specifically to get petroleum out of tight rock reservoirs. The process involves fracturing the rocks using fluids under high pressure. This creates secondary porosity, resulting in an increase in permeability. But there's more to it. To improve the performance of high-pressure water at fracturing rock, oil companies will add any of over 1,000 chemicals to promote the release of petroleum product from the sediment grains. A 2016 report from the EPA found that many of the chemical additives used in hydraulic fracturing fluids can be harmful to aquifers, especially when spills of those chemicals get directly into aquifers. Trucks with additives typically drive right up to the wellhead and can account for up to 2% of the volume of hydraulic fluid. Then, to keep the fractures open and grow the fractures even more, it's also common to pump in sand grains of gradually increasing size, accounting for 2 to 10% of the injected volume. The development of tight rock reservoirs has spurred the technology of horizontal drilling. A single well is drilled down, reaching depths up to 10,000 feet from the ground surface. Depending on the thickness and occurrence of the tight rock reservoir, a single or multiple horizontal wells are extended off the vertical shaft. This is simply an amazing drilling technology. What's clearer is that this technology has resulted in the production of major amounts of petroleum. The Bakken oil field in North Dakota, Montana, and Saskatchewan was producing over 1 million barrels a day by 2015, with a total of 3.5 billion barrels from the Bakken Formation alone by the end of 2020. And the USGS estimated it has over 3.5 billion additional barrels of technically removable oil. There could be more. Even larger, the West Texas oil plays, the largest in the US, have an estimated 20 billion barrels of technically recoverable oil. That would be slightly more than the 18 billion barrels that came through the Trans-Alaska Pipeline. Ohio and Pennsylvania are expected to see big increases in oil production as the Marcellus Shale is developed. Like any extraction process, there are problems. Injection of wastewater back into the ground during the hydraulic fracturing process causes earthquakes. States like Oklahoma rarely had earthquakes up until 1980. Now they have earthquakes regularly. A large concentration of what was inactive, very ancient faults have been activated by injected fluids. The Oklahoma Geologic Survey has impressive illustrations of earthquake frequency on their webpage. If surface structures, houses, are damaged by these earthquakes, getting reimbursed for repairs is a tricky process. Most homeowner policies don't cover earthquake damage. Perhaps the most sobering complexity of hydraulic fracturing is that most wells drilled using this method only produce for a short period of time. It's been estimated that the Bakken play in North Dakota might peak in just 5 years and decline quickly thereafter. At a certain point, you're spending more money trying to get less gas out of the ground. It's an expensive proposition. One of the standard jokes is that the U.S. has spent $1 billion on hydraulic fracturing and gotten $800 million in return. It is an interesting direction in oil production for the U.S. With production from hydraulic fracturing beginning a downward trend, will Hubbard's curve finally predict the end of oil production? The answer is maybe not, at least for a while. That's because of ultra-deepwater drilling. Again, this is yet another technology that I never envisioned as a student. Technology doesn't come about unless there is a need. The technology for extremely deep holes, the record for total depth, water and sediment, of 35,000 feet came about with the discovery of oil reserve beneath salt layers offshore. These oil plays are referred to as pre-salt reserves or subsalt reserves. The term pre-salt refers to organics that accumulated prior to the salt horizons, and the term subsalt refers to organics located under a salt layer, suggesting that maybe the salt layer was in its original location. Until recently, the technology didn't exist to assess oil reservoirs beneath the Gulf of Mexico salt layers. As geophysical techniques developed and as exploratory wells probed beneath salt layers, the industry began to realize that there were substantial reserves there. Of course, the prospect of substantial reserves, estimates suggest around half of what came out of Alaska's North Slope, drove the technology to drill deeper and deeper. Again, the technological developments come with a price. Everybody knows the Deepwater Horizon, the ultra-deepwater submersible oil well drilling rig that catastrophically blew out in April 2010, resulting in the loss of human life, the pollution of the Gulf, and the toll it took on wildlife. It was a disaster in every sense. Yet, without question though, the U.S. will continue to explore the ultra-deepwater oil plays, for better or for worse. So what's the future petroleum production levels? As I mentioned, I'm optimistic about new technologies providing fairly solid returns for a while. How long is a while? That's hard to say. Although tight rock reservoirs like the Bakken fields have been productive, we really can't depend on it for long. And that'll be the case with tight rock plays in Pennsylvania and Ohio. They'll be good, but tight rock formations just don't have the longevity that conventional oil plays have. After all, they are very impermeable rocks. The ultra-deep water reserves appear to be good, but it's hard to assess exactly how much recoverable petroleum exists because of the complications associated with assessing reservoirs through the salt layer. The bottom line remains, petroleum is a finite resource. It formed in a select group of sedimentary basins, and there is a limit to how much you can get out of the rock. We will run out. But here's something to think about. Petroleum is really a byproduct of solar energy. This is something I always remind my students. Petroleum, and coal for that matter, can be considered to be something like a trust fund. Solar energy millions of years ago was stored through the production of organic matter. And as we use fossil fuels, we are literally burning through that trust fund at a rapid rate. Of course, as we replace fossil fuels with sustainable energy sources, we are turning to solar energy in the present, whether that's solar panels or wind that ultimately gets its energy from the sun. Thus, we are extending the life of the Petroleum Trust Fund by taking advantage of energy production from sunlight today.